Thanks, Marina. Glad to be here.
Now, Perseverance is landing on Mars at the Jezero crater. Why is it that you and the team chose this particular area?
Yeah, so scientists believe the Jezero crater is one of the best places on Mars and possibly the entire solar system to look for signs of ancient life. Jezero contained an ancient lake and has within it one of the best preserved ancient delta deposits on the surface of Mars. And deltas form when a river enters a relatively open body of water, like an impact crater, and deposits the sediment that it's carrying into the lake. And we know based on studies of deltas and lakes here on Earth that they're great places to concentrate and preserve organics and support microbial life. We're also excited because Jezero exposes rocks that are between 3.5 to more than 4 billion years old and represent a variety of different geological processes.
Now, this might be a tough choice, but what do you think would be the most rewarding scientific discovery that we expect to get from this mission?
Yes, hands down, I think the most rewarding discovery I think we can make with Perseverance would be finding a truly compelling ancient biosignature on Mars. The rocks in and around Jezero crater record a period of time when life first arose in the solar system, and we have the opportunity with Perseverance to study the evolution of the planet from a once habitable world likely capable of supporting ancient life to the cold, barren planet we know Mars is today.
And why do you think, Katie, it's so important to find out if there really is or was ancient life on Mars?
Well, the question of whether there's life beyond Earth is one of the most fundamental and essential questions we can ask. And our ability to ask this question and develop the scientific investigations and technology to answer it is one of the things that make us as a species so unique. And based on everything we know about Mars in the past, it absolutely should have been capable of supporting ancient life. So we can find out an answer to the question, where there were habitable environments, was there life? And studying the possible emergence of life on ancient Mars can also help us better understand the conditions that led to life on our own planet.
That's so fascinating, Katie. Now we're going to take a question from a student, Vara.
Hi, I'm Vara, and my question is, why was Mars able to sustain lakes and rivers ages ago, but cannot now? Isn't it cold enough to make water, and isn't it always? Thank you.
Yeah, that is such a great question. And one of the things that protects our atmosphere here on Earth and allows liquid water to be stable on our own planet is the fact that we have a magnetic field protecting that atmosphere. We think that Mars lost its magnetic field way back billions of years ago and left the atmosphere exposed to things like solar winds and cosmic rays that basically blew that atmosphere away. And once that happened, liquid water wasn't stable on the surface of Mars anymore. It was too cold and the pressure was too low. And so now Mars is not capable of supporting liquid water and likely not capable of supporting life at its surface.
Well, thank you so much to Vara for that great question. And a big shout out to all the kids that are watching out there today. And thank you so much to you, Katie, for joining us. That was so great.
Thank you.
Now sending it back over to you, Raquel.
Thanks, Marina. Earlier, we were able to catch up with the communications systems engineer, Chloe Sakier. She helps us break down the system used to track Perseverance during landing.
The communications infrastructure supporting Perseverance's landing is quite complex. We've rallied a truly global network of relay and communications assets to help us capture and record those precious minutes of entry, descent, and landing, or EDL. We receive a stream of engineering telemetry via these communication assets that helps us see and understand exactly what's happening. Perseverance sends direct-to-Earth X-band tones, each of which provides us with indications of critical entry, descent, and landing events. During entry, descent, and landing, we have 2 Mars orbiters listening for the ultra-high frequency, or UHF, signals from Perseverance. These orbiters relay these signals to deep space network stations on Earth, Madrid in Spain, and Goldstone in California. The Mars Reconnaissance Orbiter, or MRO, has reconfigured its software to perform a type of relay called bent pipe. This will provide us with near real-time telemetry during entry, descent, and landing. We have coverage from the Mars Reconnaissance Orbiter from just before entry to a few minutes after landing. The telemetry we receive will be delayed by the time it takes light to travel from Mars to us back on Earth. Additionally, the Mars Atmosphere and Volatile Evolution spacecraft, or MAVEN, is recording these UHF signals and will be relaying that recording hours after landing. Maven will be covering us from around the time of cruise stage separation until a few minutes after landing. We also receive what we call heartbeat tones, which are indications that the spacecraft is alive and progressing throughout entry, descent, and landing. It's important to note that while unexpected, we could lose our communication links and still land safely. Because Perseverance is doing entry, descent, and landing completely autonomously, she doesn't need our help to joystick the landing. The communication links give us added visibility.
And you can see Chloe hard at work inside Mission Control right now. Perseverance's landing might look like the system the Curiosity rover used back in 2012. But landing on Mars is difficult. There's always a risk involved. Here's what needs to happen for Perseverance to touch down safely in Jezero Crater.
Nothing can be taken for granted when you get to Mars. There's a lot of things we just don't know.
Space always has a way of throwing us curveballs and surprising us.
I mean, until we get the data that says we're on the ground safely, I'm going to be worried that we're not going to make it.
Entry, descent, and landing is often referred to as the 7 minutes of terror because it takes about 7 minutes to get from the top of the atmosphere of Mars to the ground safely.
The spacecraft has to do all of this by itself.
There are many things that have to go right to get Perseverance onto the ground safely.
There's a lot counting on this. This is the first leg of our sample return relay race. There's a lot of work on the line.
Starting about 10 minutes before atmospheric entry, we get rid of really the spacecraft part of the rover that's been supporting us.
We come screaming in to the Martian atmosphere at 12 to 13,000 miles per hour.
And the heat shield is what dissipates all that initial energy through friction.
The vehicle will continue actually flying itself through the atmosphere. It's sort of like a transforming vehicle that went from spacecraft, and now it's kind of like an aircraft actively guiding itself.
When we're going slow enough, we deploy a parachute.
It's the biggest supersonic parachute we've ever sent to another planet. It's critical for slowing down the vehicle.
Perseverance's entry, descent, and landing borrows heavily from that of Curiosity.
But fundamentally, Perseverance is a different rover. She's bigger, she has different instruments.
We've added a lot of smarts on the inside to make it more capable so that it can deal with the landing site that we've given.
The science team identified Jezero Crater as basically an ancient lake bed and one of the most promising places to look for evidence of ancient microbial life and to collect samples for future return to Earth. The problem is it's a much more hazardous place to land.
When you look at Jezero, all you see is danger. How do we go to a site that we never thought was safe enough to go to before? So the heat shield, which has protected us all the way through entry, is no longer necessary. We need to get that off so that we can actually see the ground. And we can see the ground in a couple different ways.
Perseverance will be the first mission to use terrain relative navigation. So while it's descending on the parachute, it will actually be taking images of the surface of Mars and determining where to go based on what it sees. This is finally like landing with your eyes open. Having this new technology really allows Perseverance to land in much more challenging terrain than Curiosity or any previous Mars mission could. Amongst the rocks and the craters and the cliffs, these things are hazardous to the rover, but these are the things that are interesting to the scientists.
Once Perseverance has figured out where she is, jettison the back shell and parachute, and light up our rockets. Those rockets help us steer to a safe landing spot that's nearby.
That descent stage takes us all the way down to about 20 meters off the ground.
That's when we start the sky maneuver. Once the rover has hit the ground, the descent stage will cut loose from the rover and fly away to a safe distance. But surviving that 7 minutes is really just the beginning for Perseverance. Its job, right, being the first leg of sample return, to go look for those signs of past life on Mars. All that can't start until we get Perseverance safely to the ground. And then that's when the real mission begins.
With us now is Al Chen. He is Perseverance's entry, descent, and landing lead. Al, you were part of the Curiosity rover landing. Does it get any easier the second time around?
It absolutely does not, especially when considering we're trying to land the biggest, heaviest, and most complex rover we've ever built. They're all over the place, rock fields. That would be a bad day for us if we were to land on them.
Now, Al, what new technology makes this type of dangerous landing possible?
Perseverance is carrying two new technologies that are really kind of under the hood smarts that are allowing us to land at this treacherous landing site. The first is range trigger. That's the ability, we've given Perseverance the ability to decide for herself, based on where she is, when to deploy the parachute. Previously, we used to deploy parachutes, that supersonic parachute, based just on navigated velocity. But now Perseverance has the smarts to figure out where she is and deploy that parachute at just the right place to make sure that we shrink where we could come down. That actually reduces the area, that error ellipse, where we can come down on the ground, from something that was on the order of 15 miles long by 12 miles wide for Curiosity to about 5 miles long by 4 miles wide for Perseverance. So that's quite a bit of reduction. Second, the next piece of technology that's helping us land there is terrain relative navigation. In the past, after we've popped off the heat shield, we've taken pictures of the ground as it's been coming up, but we haven't really done anything with them. This time, Perseverance is carrying a camera to take pictures, but also a kind of second brain to help it figure out what those pictures are telling it and match it up with an onboard map from a satellite. That allows it to figure out exactly where she is. Suddenly then, she can then fly to safe spots that are nearby once she really knows where she is. It allows the site to not have to be as flat and boring as a pancake as some of our past sites have been, the entire area we could come down. Now we just need little pieces of that site to be small enough and safe enough for us to land in safely and fly there after we've gotten rid of the parachute.
And we also have a social media question coming in. Sansakari14 on Instagram is asking, how does the sky crane decide where to move itself after the payload lands?
After the payload lands, after the rover touches down, the sky crane, the descent stage, which is that rocket-powered jetpack above it, the first job, of course, is to make sure you don't hurt the rover. So it'll turn forward or backward so that the engine plumes don't pass over the rover. So it'll come up and start to turn. And it'll go in whichever direction is closest to north. So it can either go forward, if that's the way north is, or go toward the rear of the rover, if that's where north is. And it'll fly about 1/3 of a mile or so away.
Thanks for talking to us today, Al.
Thank you very much.
Now, let's head back to Mission Control for an update from Swati.
Hi, Raquel. So remember that command that we sent at around 11:35 to turn the transmitter off? We are just about to get confirmation that Perseverance has received the command. The command took 11 minutes to go to Perseverance, and then the reply took 11 minutes to get back from Perseverance to the ground. So we should hear any second now that we have officially turned off the transmitter. And after that, we will be about 4 minutes from the start of entry, descent, and landing mode. At this point, we will transition from the cruise approach mode to entry, descent, and landing. And that means our travel from Earth to Mars is done, and now we just need to get to the surface. So far, things are looking good.
Great.
Oh, this is Pad 3, ready to show estimated miss distance for OD 132.
Copy, EDL phase, we'll come back.
Flight Ace.
Go Ace.
Our tracking stations have all confirmed the results of the transmitter drive off and in lock one way.
Copy, Ace. GDS flight. Flight GDS. At this time, I'd like to disable the alarms before EDL main. So please disable all the alarm files and start a new downlink session. Copy that, EZP. Copy that, proceeding now.
Confirmation that we are now officially one way and the transmitter is off.
Rover mission has helped shape the other, starting with the landing of the Pathfinder more than 20 years ago, leading up to where we are today with Perseverance. Perseverance Deputy Project Manager Jennifer Trosper has worked on every Mars rover mission, and she joins us now. Jennifer, how does Perseverance fit into the history of exploring Mars?
Thanks, Raquel. It's great to be here. Well, Perseverance is NASA's 5th rover on Mars, and I've had the privilege of working on every one of them. And the very first rover was the Sojourner rover we sent in 1997, and it was the size of a microwave oven. And even at that small size, Sojourner was able to transform the way that we explore Mars, from stationary landers to small roving robots that go from place to place, just like a geologist would on Earth. So once we had that roving capability, then we sent our twin rovers Spirit and Opportunity. Spirit and Opportunity were tasked with finding evidence of ancient water on Mars. Now they did. They're great explorers, and both of them found ample evidence that water had once existed on the surface of Mars. But we had a question. Another question then was Mars ever habitable if water had been there? And that's when we sent Curiosity. Now Curiosity was a major upgrade to our rover fleet. She's the size of a small car. She landed with the Sky Crane system instead of airbags. And she also carries along her own sample analytics lab, and she's still operating today. And during her exploration, she has found evidence of a habitable environment in an ancient lake bed on Mars. So now we're sending Perseverance. Perseverance is tasked with answering the question and looking for evidence of ancient microbial life on Mars. And in order to do this, she has to be the smartest and most capable rover we've ever sent.
Speaking of Perseverance, can you tell us more about how Perseverance is smarter than its predecessors?
Yes, we've made a lot of upgrades to help her along with the surface mission. One of them is for her autonomous traverse capability. When I say autonomous traverse, I mean we tell her where we want her to end up, and she has to figure out the safe and best way to get there. In order to do that, she uses her cameras, algorithms, a computer. So we've given her another computer, we've upgraded the cameras, and we've upgraded the algorithms. Now she drives 3 times as fast as Curiosity could drive in this autonomous traverse mode. In fact, her average daily distance for driving, about 200 meters, is close to the maximum distance any rover has ever driven in a day on Mars. So she's fast. Another thing that we've done, which is the most significant upgrade that we've made, is the sample caching system itself. Curiosity has a robotic arm, like Perseverance has a robotic arm, but on the end of Perseverance's robotic arm is a coring drill that will go and take rock cores, transfer them into sample tubes and into the rover, where another robotic arm will take those tubes, will seal them and store them, and eventually drop them on the surface of Mars for future return to Earth.
Great. And we also have a social media question about Perseverance. Erica AS on Instagram wants to know what the wheels of the rover are made out of.
Great question. Well, you may think we make them out of some material you've never heard of. It turns out they're made of aluminum. Now, Perseverance's wheels are a little thicker than Curiosity's, but they're actually both made out of aluminum.
And one more question for you. Can you tell us more about the importance of where you are right now in the building?
Yes, I am above, on the 2nd floor, above the cruise mission support area that you've been watching. And this is the surface mission support area. So as soon as Perseverance lands, all commands, this room will take over. It will become headquarters for operating Perseverance on Mars.
Thanks for taking the time to talk to us today, Jennifer.
Thank you.
Now, we now know Perseverance's place in history. Let's take an up-close look at the rover with Mars 2020 System Testbed Engineer Elio Morillo.
Thank you, Raquel. I'm standing in front of the Mars 2020 Perseverance scaled model. As you can tell, this vehicle is about the size of a Mini Cooper. These wheels are obviously black here and they look like rubber, but they're actually fully made of metal. These wheels are designed to allow us to climb over obstacles and of course climb over hills and minimize the amount of slipping once we're traversing on the surface of Mars. Here in the front of the rover, we have the sample caching system. And of course, at the very front end of this is the robotic arm, which this entire system is arguably the most complex robotic system we've ever sent outside of Earth. Here at the tip of the arm, we have a turret which contains a suite of instruments along with some drills and coring capabilities that will allow us to do contact science once we get to the surface of Mars. Not only that, this robotic system is equipped to collect samples about the size of a piece of chalk that then eventually will be stored inside of the vehicle and dropped off in a later location so that an eventual mission can go and return these samples to Earth, something we've never done in the past. Here in the front, we have the remote sensing mast. Something of note is that this mechanism is going to be stowed upon the touchdown on the surface of Mars. And one of the first critical activities we do is deploy this mechanism. This mechanism includes several cameras that are going to give us some of the most breathtaking images we've ever taken on Mars. Along with that, we have some lasers as well as a spectrometer. They're going to allow us to do some remote science. Here you see some of these extrusions that are part of a larger weather suite of instruments that will allow us to characterize the local climate around Perseverance. So that's a quick tour of the rover, but I gotta get back to work. So back to you.
Perseverance is collecting samples of Martian rock for future return to Earth. We've heard that scientists have been wanting to bring Martian samples back for many generations. And here to talk a little bit about that is NASA's Planetary Science Division Director, Lori Glaze, who joins us now to talk about the role Perseverance will play in NASA's future goals. Welcome, Lori.
Hi.
Now, as you just heard, we've heard that scientists have been wanting to bring back these Martian samples for a very long time. Why do we need to bring them back?
That's really a great question. You know, we actually have examples of Mars already here on Earth that came here as meteorites. But we don't know exactly where they came from on Mars, and then they also have had to make the trip from Mars to Earth, and so they got altered during that time, and then during their entry and descent into the Earth's atmosphere, that also changes what those rocks are like. So being able to go to Mars and actually collect a sample where we know exactly where it came from, and we know we can preserve it and keep it pristine and carry it all the way back here, this will be incredibly important to help us answer questions about the geologic history of Mars, understanding how it formed and evolved, and also really important questions about whether or not life actually existed on Mars 3.5 billion years ago, and whether that life, if it existed, has been preserved in the surface of Mars.
Now, Lori, these sample tubes that Perseverance is going to be collecting, they're the cleanest things ever created on Earth. Tell me a little bit about that.
Oh my goodness. We worked so hard. The team here at JPL is absolutely incredible to assure that those sample tubes are incredibly clean. One of the main goals of this mission is to be able to detect if there's actual life that's preserved, ancient life preserved in those rocks, in those samples. And we definitely don't want to be carrying, our own DNA off to Mars and then bring it back here to confuse our scientists when they're trying to study those samples. So it is an incredibly clean set of equipment that's been sent there. As you said, the cleanest thing we've ever sent into space.
Now, this is a very complicated campaign. Can you break down for us how it's going to work and if there's any international partners working with us?
You are correct. The Mars sample return campaign is incredibly complex. In fact, it's probably the most challenging thing we've ever tried to do. But we're definitely not going to try and do it alone. We have great partners with the European Space Agency. And the way this campaign is going to work, well, Perseverance is the first step. Chapter 1 is going to Mars and collecting the samples. Chapter 2 is going to be a sample return lander that we hope to launch in around 2026 to 2028. And that lander, it'll be an American lander carrying a fetch rover that's provided by European Space Agency. And that little fetch rover will drive out and pick up the samples that Perseverance left on the surface of Mars. And the fetch rover will bring them back and load them into a rocket that we call the Mars Ascent Vehicle, which will be the first ever launch from another planet. And it will launch those samples into orbit around Mars. In the meantime, European Space Agency will have an orbiter that's in orbit around Mars that can rendezvous and capture those samples and then bring them back to Earth for us to study back here in our amazing laboratories.
A lot of firsts, it sounds like, Lori. And another first, how is Perseverance and the Mars Sample Return mission going to help the future exploration, human exploration of Mars?
I'm so glad you asked that. I think we're going to get a lot of great information from Mars Sample Return with, again, being able to land the heaviest payload we've ever landed on Mars will be that Sample Return lander. That's critical to us learning how to land humans on Mars. And then we are definitely going to want to be able to launch the humans back off of Mars. So that Mars Ascent Vehicle is going to be critical, that first step of the first launch from another planet.
So exciting, Lori. And speaking about the Mars generation, we're now going to take a student question for you from Livia.
Hi, my name is Livia, and my question is, what made you want to study Mars, and why are you working so hard and willing to wait so long for a sample? Thank you.
Oh, Olivia, that is such a great question. And I enjoy Mars just because it can tell us so much about how our solar system formed and evolved. All of the planets can tell us different parts of that story, and Mars is a really key piece of that. And one of the main reasons we're willing to wait so long to get the sample back is that we've got great new scientists that are all about your age, and in about 10 or 15 or 20 years, you'll be the generation that's going to actually get to work with these samples. When they come back, you'll be the scientists and engineers that will be the next generation to change how we think about Mars and how we think about life in the solar system.
That was a great question, Lori. Reach for the stars, future little scientists and engineers. Thank you so much for joining us here today, Lori.
It's my pleasure. Thanks.
Back to you, Raquel, for another mission update.
Thanks, Marina. The cruise team for Perseverance controls the rover on its way to Mars. And moments ago, they handed it over to the landing team, and it looks like team leaders in mission control are about to talk to both teams. So let's listen in.
The CBM change, as I mentioned previously, is to the EDL reserve to a non-coherent route.
Activity.
Copy flight.
EDL phase, go ahead.
I think I'd like to see pep talk, I guess, to the team. All right. You know I'm terrible at pep talks. I think my reputation precedes me there. And look, I know this hasn't been easy, right? I'm not even sure we've even been all in the same room at the same time. I mean, I'm staring at folks across the internet as well. Even now, right? Yeah. Voice check. Okay. I do want to just extend my heartfelt appreciation from the EDL team to the launch cruise team. You've done everything we've asked for, right? I mean, you've battled anomalies, you've dealt with Cepheids, you've done everything. You delivered a healthy spacecraft to the place that we want to go, and she's right on target, right? You did the last maneuver literally 2 months ago, right? This is pretty incredible, in my opinion. And she's armed with the right information to help us land. Doing the parameter update last night